In the second part of the lecture, we are going to talk about the dimensionality reduction, feature extraction, and manifold learning. So we will talk about how the dimensionality reduction can be used, and then we will talk about feature extraction and manifold learning. Transforming data using unsupervised learning can have many motivations. The most common motivation is that we can visualize the data uh, in the low dimensionality. We can compress the data and find the representation of data that is more informative for further processing. One of the simplest examples of the why the one of the simplest and most widely used algorithm for all these purposes for dimensionality reduction and feature extraction is the principal component analysis. We will also talk about the other two algorithms, which is non-negative matrix factorization, which is commonly used for feature extraction, and t-SNE, which is commonly used for visualization using two-dimensional scatter plot. T-SNE is used actually for visualization of the data. So first we talk about the principal component analysis. PCA is a method that rotates the dataset in such a way that rotated features are statistically uncorrelated. They have no relationship with each other. They become uncorrelated with each other, statistically uncorrelated. Rotation is often followed by selecting a subset of new features. We select subset of new features, we choose new features, and according to those features, according to how important they are for explaining the data, and find that how those features are important for the explanation of the data. The following example illustrates the effect of PCA on synthetic dataset. So we apply the we learn a command. I executed a command, and it generated a 4 different plots. Okay, we talk about these 4 plots. This is the original plot of the PCA, where the plot is used for 2 features. This is the feature 1, and this is the feature 2, and this is the transformed version of this data. And then here it is the transform data with respect to second component, and second component is drop, and this is the back rotation by using the, we talk about what these things are. So the first plot shows the original data points. These are the original data points, and distinguish among them. The algorithm proceeds by first finding the direction of maximum variance, and it is called as a component 1. So this is the component 1, where is the highest variance. This is the first component of the PCA, where the highest variance. This is the second component of the PCA, where the variance is low. And these two components are uncorrelated with each other. They are orthogonal to each other. They are perpendicular to each other. The direction in the data that contains most of the information, or in other words, the direction along which the features are most correlated to each other. This is the direction where the features are correlated, but the orthogonal components, component 1 and 2, they are uncorrelated with each other. The algorithm finds the direction that contains the most information while being orthogonal to the first component, orthogonal to the first direction. So second component is orthogonal to the first component or first direction. In 2 dimensions, there is only one possible orientation, that is a right angle or perpendicular, but in high dimension, the shapes could be infinitely orthogonal directions. In high dimensional, there could be many different possibilities, but we can't visualize more than 3 dimensions. So we have to restrict ourselves or 2 dimensions or 3 dimensions. Directions found such a way are called principal component. These are the principal component 1 and component 2. Second plot shows the same data but now rotated to the first principal component coincides with the x-axis and the second component coincides with the y-axis. The average is subtracted from each data before rotation, and converted the data to centered on 0. So the mean is subtracted. So this is the same data shown over here, but what we have done, before the rotation, we have subtracted the average is subtracted, mean is subtracted, and converted the data along the zero, centered along the zero, and such that the first component is in parallel with the first component of the PCA is in parallel with the x-axis, and second component is in parallel with the y-axis. So this is the way that we have we have plot the PCA components on the this plot, and this is a transformed version of this plot. And then we talk about, we can use the PCA to downsize while keeping only the main component. So we can downsize, we can keep only the main component and drop the and leave the, we can only leave the first component as shown in the third plot. So we only leave the first component and we drop the second component, remove the second component. And this will reduce the dimension of the data. From a two-dimensional data array, we obtained a one-dimensional array. Originally, it was a two-dimensional data array, but now we have got only one-dimensional data array because we have removed the second component of the PCA. However, it should be noted that instead of leaving only the initial features, we can find the most interesting direction and leave it, that is the first component. So we can find the most interesting direction. So we can again rotate it. What we can do, finally we do the rotation, undo the rotation. This was the original representation. Then we made a rotation, and then we removed the second component. And now we are going to undo this rotation. We are going to align it in the original direction. So how we do that? We can undo the rotation and back the mean value to the data and add again or add back the mean value to the data values. As a result, we get the data shown in the last plot. This is the way we get the this plot, the fourth plot. These points are located in space of initial features, but we have left only the information contained in the first main components. Now this is the only information. This is the only information that is contained in the first component. This transformation is sometimes used to remove the noisy effect from the data. So this kind of data transformation is used to remove the noise from the data, or or show which important information is retained when using the principal component. So this is the application of the dimensionality reduction, or PCA, for noise removal. Applying PCA to cancer dataset. Now what we do, we apply the PCA for the cancer dataset. One of the most common application of PCA is visualizing high dimension data. We can visualize the high dimensional data set. We can, as we saw earlier, it is hard to create the scatter plot of data that has more than two features. If we have the two features, we can make a scatter plot. And if you recall the previous lectures, I guess lecture 2 or 3, we used the iris data set, and we made a plot of iris data set, feature plot of iris dataset, scatter plot of features for iris dataset, where iris dataset has only 4 features: sepal length, sepal width, petal length, and petal width, and we get the 16 plots, and then we analyze those plots. But for talking to the breast cancer dataset, we have 30 features, and we have dataset has 30 features, and which could result in 13 multiplied by 420 scatter plots. So we get the 420 scatter, and we would never be able to look all these scatter plots. So we try to remove to find some other way how we can understand this representation or this data set. Using PCA, we can get the first two components and visualize the data in these two-dimensional space with a single scatter plot. Before we apply PCA, we scaled our data so that each feature has a variance of 1 using standard scalar. So we use the standard scalar, and we import the breast cancer data set, and we make an instance, and then we apply the to the answer data set, we apply the standard scalar and scalar fit and transform. Learning the PCA transformation and applying it in a simple way as a pre-processing transformation. We instantiate the PCA and then apply the transform, all these things. PCA rotates the data but keeps the all the principal components. To reduce the originality of the data, we need to specify how many components we want to keep when creating the PCA. So we have to mention that how many components we want to keep. So PCA components, we only want the two PCA components. Original data has a shape of 569 class 30, 569 instances, and each instance has 30 different features. But now we have reduced the features from 30 to 2, and now the reduced shape is 569 instances, and each instance has 2 features. So now we are going to plot this data, and we are going to show and visualize this data. And this is the plot of the data using principal component analysis and considering only the first two component 1, principal component 1, and principal component 2 for the breast cancer data set. And this is the plot. And if you remember the breast cancer data set, we have the malignant class and we have the benign class. This is the benign class and this is the malignant class. And you can see that there is a separation in these two data sets. And if we want to apply some linear classifier, a linear classifier can easily classify most of the points. If we can draw the line over here, so it can classify most of the malignant class from the benign class. It is important to note that PCA is an unsupervised method and does not use any class information when finding the rotation. It simply looks at the correlation in the data. For the scatter plot shown here, we plot the first principal component, this is first principal component, against the second principal component, and then use the class information to color the points. That we have the malignant class and we have the benign class and malignant class. You can see that these two classes separate quite well. These two classes are separated from each other, where this leads us to believe that even a linear classifier can be used to classify the data. We see that malignant class blue points, they have more scatter, as compared to benign points. A downside of PCA is that two axes in the plot are often not very easy to interpret. And PCA, we can't say that what this principal component 1 means, what this second principal component means. So it is difficult to explain. Components, principal components to the directions. It is important to note that the unsupervised is only class. Okay, the two axes in the plot are not easy to interpret. Two downside of PCA is that two axes are not easy to interpret. A principal component correspond to directions in the original data, so they are combinations of original features. So all the PCA attributes, all the PCA components, they are stored in the components underscore attributes. So if we want to check that PCA shape, it is 2 cross 30. It is 2 cross 30, that we have two features for out of 30, we are using only 2 features. Each row in the components corresponds to the principal component, and they are sorted by their importance. The columns corresponds to the original feature attribute of PCA, mean radius and texture. So here we are going to print principal components. So these are all the principal components. We can visualize the coefficients using heat map. So we visualize these coefficients, and these are the different coefficients. This is the first principal component. It has dimension of 30. This is the second principal component. It also has a direction of 30. So we can see that the first component, all features have same sign. So all features, they have almost the same sign. Like here, all features, they are almost like the same sign, but there is less variation. But if we talk about, this means that in general correlation between all features. The first component, it finds the correlation between all features. Correlation in the all features it finds. The second component, one measurement is high, the other is likely to be high as well. So in the second component, so for example, it covers one stream. This is the one stream minus 0.2. The next box is plus 0.2. This is minus 0.2. The next is plus 0.2. So there is a high variation in the second component, has a mixed signs, and both of the components involve all the features. So there is a high variation in the second principal component. So this was the understanding and discussion about the principle. Next, we use the how PC can be used for feature extraction in the next part.